this is on a problem set, yes, that was handed out yesterday. I'll have to help you in a minute. I'm right in the middle of this. Okay. So, we have a situation where the commuter backs a car out of the garage to cause acceleration to this. And we want to know how much time it takes for her to reach this speed. And then she brakes to a stop at this. And they're asking what is her acceleration, deceleration during that time. So, first thing on our Y, a couple things that really we need to have in there is the idea, what happens if your velocity, well, how fast is she going in her garage? How fast can we assume that she's going when she's just sitting in her garage? 0. So I'm going to assume she starts from 0. Right? That's a pretty fair assumption. She starts from 0. And then as she's backing up, her acceleration and her velocity are in the same direction. So what does that mean? What does that do to her speed? Makes it go up. Good. So if accel and velocity same direction, speed increases. Sorry, ran out of room there. What if the acceleration and velocity are in opposite directions? Like after she gets out of there. What if she's moving that way and she accelerates the opposite way? What does she do? Does she keep speeding up, or does she slow down? She slows down. So speed decreases, or she slows down. Slows down. And it says eventually she comes to a stop. How fast is she moving as she stops? 0. Right? So I think those are the crucial understandings to have in your Y. That she starts from 0. When the acceleration and velocity are in the same direction, the value, the speed is going to increase. If they're in opposite directions, her speed is going to decrease. Remember, acceleration describes the rate the velocity changes at. All right? So, one thing you can do in the how, that if it's useful to you, I like to draw pictures. I'm going to skip the picture this time and look at some of the things I know. For part A, I'm going to kind of do an inventory. I know that we said she started with a velocity of 0 meters per second. They say she gets up to her V final 1.60 meters per second, right? Her acceleration is 1.40 meters per second. The time, we don't know, right? So, and that's probably the other thing I could have up here in my Y, is that acceleration is the rate of change of the velocity. Sorry, so that would be a good thing to have up in your Y there also. And so I'm looking for an equation that talks about how my velocity changes as I accelerate for a certain amount of time. And that's this equation here. So, grab that. So now, substituting into that, let's see, my V final is 1.60 meters per second. My V initial is 0 meters per second. Plus my acceleration is 1.40 meters per second squared. And I don't know my time. It's squared because acceleration is describing the rate the velocity is changing. So it's saying every second it's changing by this many meters per second. So that ends up being meters per second per second. Just like speed is describing, or velocity is describing the rate your position is changing. So it's saying for every second it's going this many meters. That makes sense? You mean which formula goes with which idea? Okay. Well, remember, we practiced a little bit yesterday reading the formulas, converting them from math to English. And so like this one in English, I would read as the speed or velocity I end up at is, let's do it for velocity, okay? The velocity I end up at, that's that V final, is the velocity I started at, and how much it changed because I accelerated during that time. By being able to translate from math to English. That's what we're learning right now. That's part of the process of learning this. Is being able to look at these and have the concept behind it. The concept behind this relationship is that the acceleration is the rate the velocity is changing. So how much it changes depends upon how long you accelerate for. So this is saying, this is that relationship. This comes directly from our definition of acceleration, the change in velocity per time. All right, so it's understanding that relationship, and then you can hopefully better understand these sentences. Yeah, probably coming up next week. I'll outline all that on the Google Calendar, okay? So, now, I only have one variable left. I'm good. I can solve this, right? My acceleration is saying that for every second, my velocity is going to change by 1.4. I'm going from 0 up to 1.6. Just without a calculator, about how long is that going to take? If every second it changes by 1.4, and I got to get to 1.6, it's going to take less than a second, or more than, huh? No, 1.08 or something. Yeah, something a little bit more than 1. Excellent. So now we've got in our mind, hey, I've got an idea. If I get a number like 2 million, I messed up somewhere. But if I get a number close to 1, I'm probably right. So now it's just doing math, right? That just disappears. I bring the 1.4 meters per second squared over the other side. I'm not sure how good your algebra skills are, so I'll write it out. Over 1.40 meters per second, and I'm going to write that as meters per second per second. That equals t. And if I do in my calculator, the number part comes out to 1.14, and then unit-wise, meters per second, cancel out meters per second. So I've got over seconds. Oh, so the seconds come up, and there's my answer, 1.14 seconds. And it's within, the idea I was thinking of, a little bit over 1. Yeah, I think it's right. Sure. Yeah, that's right. You guys saw I published the answers to all this, right? Oh, in our documents folder, you'll find, it says all the answers are there. So you can check. Kind of neat. Oh, where's the documents folder? Where do you think? Physics is fun. And it says the document. Look at that. Isn't that annoying that all that's right up there? In part B here, she's now braking to a stop in 0.8 seconds. So if I do my little inventory, I know the B final, she's stopping, so that's 0 meters per second. She's starting just from where she was, so that's at 1.60 meters per second. Her acceleration is, I don't know. Okay. Let's continue on with this one. We're right in the middle of writing down doing a little inventory. And they told us that T is 0.8 seconds. Oh. I think I'll use the same relationship. What do you guys think? I'll use the same relationship. Let's see. There we go. Pull it down. Guys and gals, you paying attention? Or are we done with this one? We should move to the next one. What do you think? Okay, we'll finish this. The first one, we did that one in class. Okay, why don't you look at C-Blocks? C-Blocks video has it perfect. So I'm going to end up at 0 meters per second. I'm starting at 1.60 meters per second plus A, and I do that for 0.8 seconds. Oh, my speed slow. Now I'm moving positively, and I'm slowing down, so I expect my acceleration to be positive or negative. In the same direction as I'm moving, or opposite my motion? Opposite, right? We wrote that in the Y. And so I'm hoping I get out a negative number, right? Fingers crossed, ankles crossed. So, negative 1.60 meters per second equals A times 0.8 seconds. Negative 1.60 meters per second over 0.8 seconds. That gives me A equals negative 2.00 seconds. Oh, not second. Is my math wrong? Meters per second. Per second. Yes, that is. Oh, sorry, my O's. All right. Number 7. Car accelerates from 18 meters per second to 35 meters per second in 10 seconds. Assume constant acceleration. What was its acceleration? How far did it travel in this time? So, first thing to make sure we show our understanding of is, what is acceleration? Right. Acceleration is the rate, the velocity changes. So since the first part's about acceleration, it's good to show that you understand that. And then how far did it travel this time? I think what's important to realize is that velocity and acceleration influence, what's a good word? Influence how far something travels in a given time. So the faster something's moving, or the more it's accelerating, is going to change the how far it travels in a given time. All right. So those, I would say, are the two main ideas that you'd want to express in your Y. All right. So you showed why it's happening. The acceleration is, we have to look at that as finding out the rate that this speed is changing, the velocity is changing, and then second part of how far it's going to travel is going to be affected both by whatever velocity it was at and its acceleration. So if we go do the first part, equation-wise, I'm interested in how the velocity is changing at a certain time because of a certain amount of time. And that's what the relationship we were just using tells me, right? So if I grab that one again, that's talking about change in velocity due to acceleration in time. That's what I'm going to use for this first part. And you want me to do the inventory again or just substitute in? Do the inventory? Okay. So let's see what they tell me. They tell me it starts at 18 meters per second. It ends up at 35 meters per second in 10 seconds. And they want to know about the acceleration. So substituting those into this relationship I just put, 35 meters per second equals 18 meters per second plus A, which I don't know, times 10 seconds. Yes, no, good, far. So I need to get A by itself. So my first step would be 35 meters per second minus 18 meters per second. That would equal A times 10 seconds. And let's see, 35 minus 18 is 17 meters per second equals A times 10 seconds. And so I'm going to divide both sides by 10 seconds. Remember, if you miss any steps, the videos are posted up online. If you're looking at through your problem going, how did I get there? You can quickly look it up. So 17 meters per second divided by 10 seconds gives me 1.70 meters per second. Use the cross cancel out. And that equals A. So there's my acceleration. Remember, I could write meters per second as meters per second squared if I like that notation better. They both mean the exact same thing. Right. Shall we go on to the second part of this one? Sure. So the second part says how far did it travel during this? And my main equation here talks about, remember we talked about this one yesterday, where I end up is where I started and how far I went because I was moving when I started and how far I went because I accelerated during that time. So I could look at it that way. Actually, I could also look at it using this other equation that we have in kinematics, which says how fast I end up going is how fast I was at the start and how much it changed when I accelerated through a certain amount of distance. Okay? So we could actually use either one. I'm going to use the top one. So I'm going to grab that one. Because out of the two, I feel like using this. But I could use either one. Either the first one I put into or the second one. So either this one which I described or this one. Either one, you could use it for the second part here. But in our Y, we also said, how far you go is affected by your speed and your acceleration. And that's more about this equation. So, let's see. I don't know where I end up. Where did I start? Where can I assume that I started? At 0, right? Because I can put 0 anywhere I like. When I started off, I was moving at 18 meters per second. The amount of time I moved for was 10 seconds. And let's see, what else do I know? Oh, I know my acceleration now, right? My acceleration, I just figured out 1.70 meters per second. Oh, cool. I've got all the variables, all the values set to the one that it asked me to find. That's kind of neat. Sure, they're back in the file cabinet or available also online in the documents folder. The one file cabinet, the gray one that's in the back of the classroom, in the top drawer. We're doing the second part of the problem that we've been working on for the last couple minutes. So, all right. So now substituting those values into here, D. I'm going to move that over just a little bit, make life easier. D equals D naught, which was 0 meters, plus 18 meters per second times 10 seconds, plus 1/2, 1.70 meters per second, And I'm still going to run out of room. Times, sorry, I ran out of room, 10 seconds squared. Are the 3 equations on the sheet the 3 that we've learned so far? Yes. There's also the 2 definitions of velocity and acceleration. Remember, I'm building up the equation sheet as we hit topics. So all we've done so far is kinematics. And so that's why our equation sheet only has a box about kinematics. If you look, the rest of this stuff is all math and constants, things to help you out so you don't have to memorize those even if you have. Right? Just to help you out there. As I said before, yes, those are always available for you. Tests, homework, road trips, whenever you'd like. You have them all the time. All right. So, let's see. Let's do some of the, I'm going to do the math and the little parts first, right? So D equals, at 0 meters, I can just forget about that. 18 meters per second times 10 seconds becomes 180 meters. Well, what if I'm taking 0 and I'm adding things to it, how much is it going to affect? Because, good question. Let me do it in a different color down here. When I have meters over seconds, and I multiply that by seconds over 1, because 1 second is on top and 1 is on the bottom, they can cross out, leaving me just with meters. So, that's why. Good question. There we go. All right, plus 1/2. Oh, I need my calculator now. Let's see. 0.5 times 1.7 times 10, and the 10 is squared. So I get 100.85. Now let's see, I have meters per second over seconds multiplied by seconds squared over 1. That gets rid of one of those, that one gets rid of the other one, and I'm left with meters. Cool. Meters plus meters is good, right? Let's see, 0.5 times 1.7. Oh, I did that wrong. You guys didn't even catch me. It's not 100, 0.85. I hit the wrong key on my calculator. 0.5 times 1. times 10 squared is 85 meters. Add that to 180, and I get 265 meters. My answer. That's how far it traveled during that same amount of time. All right, we're going to do number 6 here, and we only have a few minutes, so I want to do a quick. The y here for number 6, very similar to the last one we just did. Acceleration is the rate the velocity changes. And along that same line, velocity and acceleration influence how far the car travels. And the other part is, if it's slowing down, what does that tell us about our acceleration and our velocity? They have to be opposite. Yep. So that's kind of a key thing to have in here. Acceleration and velocity are opposite. And the other general fact you should know, and you don't necessarily have to write it down there, is that when you come to rest, what's your velocity? 0. Influence. Sorry. I got really messy and writing quick because I'm. So let's do our do a little picture. Car. Oh, I didn't give it a windshield. When something stops, you know, when something stops, its velocity is 0, right? That's one of those things. This is 83 meters here. And so we know that its acceleration has to be in the opposite direction of its velocity, right? So which direction do you guys want to call positive? To the right or to the left? And before you answer, it doesn't matter as long as we agree. To the right? Okay. So we're going to call this direction positive. That means that the 83 meters is positive, the 16 meters per second is positive, but we expect a negative answer we want a negative acceleration when we put it in, all right, because it's going in the negative direction. The equation that I'm going to pick is this one, our other last kinematics that we hadn't used yet today, because it talks about the velocity I end up at is the velocity I started at, and how much it changed because I moved the distance while I accelerated. So it combines this idea of changing velocity with acceleration and distance. So my final velocity here is 0 meters per second. I need to remember my grammar, that's squared. My initial velocity here was positive 16 meters per second. Don't forget my grammar, square that. Plus 2 times negative a, and then my displacement, which is 83 meters. Good so far? Well, I took my value, I didn't write an inventory this time. Just to show you a different way to do it, to line up the values. And then I substituted in to the places. Now, well, I wanted something in my y. I said that, you know, the distance affects the change in velocity, and that's what this equation talks about. I end up at this speed because I started at this speed, and it changed because I accelerated through a distance. So if I understand that that's what that equation is showing me, that relationship, that speed changes because you accelerate through a distance, then looking at this one, I say, oh, the speed changed because they accelerated through a distance, I can pick that equation. Oh, you're having trouble with the alphabet. V final means the velocity at the final, at the end. Final and V initial means beginning. So that's the velocity at the beginning. Oh, that's just math grammar. You know, that the squared term means you take whatever value you have for V and you multiply it by itself. So mathematically, it's telling me I have to square that term. So now the derivation of where that comes from, I can show you, but my guess you'd be bored with how did they end up with that squared. But how am I going to mathematically solve this? Well, I have two terms added together, so I need to bring one over to the other side. Yes, but time's always going to be a change. So just take, they said it happened 10 seconds, that's delta t. They don't tell you, like, it took from 3 o'clock to 4 o'clock. So mathematically, I need to get these two terms apart. So I'm going to bring this term over on the other side, and that'll make, when I bring something over on the other side, from addition, I have to make it opposite sign. So I'm going to get negative 2 times negative a times 83 meters equals 16 meters per second squared. What's negative times negative? Positive, right? So 2 times a times 83 meters is going to give me a times 166 meters. And that equals 16 squared. 16 squared. That's why I have a calculator. 256 meters squared per second squared, because I have to do the math for the units also. And so my A is, let's see, divide that by 166, and I get 1.54 meters per second squared. And that is my answer for this one, as long as I didn't screw up my math, which I didn't. And I know that that's in the opposite direction of the velocity.